interesting.
Yeah.
Yeah.
So yeah, this is where we have our Friday events. You can access it using your PC, which is going to be just a web browser, or you could join using a mobile phone or a VR headset.
Mm-hmm.
Check out the lounge. I think it's one of the most visually interesting places. So it's like a relatively small space, but it's like 4 rooms and big passages on your right and on your left. So it's not big, but it's rather cozy for if you have like a talk show. I don't think that you need a bigger space.
Is it like default space, or it was
No,
created by?
customized. No, it's not customized.
Yeah.
We are going to have another customized one, but this one is one of the default choices.
Mm-hmm.
Yep. So we can go straight to auditorium, which is normally a spot for us to have a conversation because I can share the browser and all of that. But I like to use these passages, like floating passages with these particles that can take you to the same place but with a different route. So it's a nice area for contemplation, right? You can see the water down there, which is kind of calming.
I like the lighting.
Yeah, the lighting, the colors, everything. Like, look at the avatars. They look detailed, but last time we had like a very decent conversation that I didn't pay much attention to because I was still dealing with first-hand problems. Like, this is a gallery, so you enter the gallery once you finish the walking.
Mm-hmm.
So, what was I saying? Is that actually last time we talked to one lady. Her name is Athena, and she's like around her late maybe 50s, mid 50s or something like that. So she's one of the organizers of the Burning Man festival. So she's like she carries the culture of it. Pay attention to the walls. Actually, it's a gallery, so we can actually generate NFTs and put them on walls. We can actually put some like photographs or pictures, present NFTs. So this space could also be a shop or something like that where people can come and buy something. Aren't we coming just from gallery? Are they 2 galleries? Yeah, there are 2 galleries. I never realized that. Is that Alona or your mom?
Mom.
Yeah, say hi to your family. I promise to visit you guys whenever I come to Nalchik, but I haven't succeeded at that so far. So yeah, what we discussed last time with this lady, she pointed out the thing that I didn't think of. She said that the communication here, like the social element of this platform, is terrible, because that
Why?
Even when we will realize with that when we start talking, because what we had in Outspace is not present here, the human contact. The eye contact is one of the most important, ways to understand that a person is listening to you, right? So here's the auditorium. This is where we normally meet and have some, different stuff. So share screen. Весь экран. Разрешить. So yeah, here it is. You can see the demonstration of my screen. So we could watch some video or something like that. Theory of everything. There's a nice video which is about geometry, so maybe we can watch that one. The one that I sent you into the chat. We still have like 20 minutes, so maybe we can watch like a good half of it actually, maybe 15 minutes or something. Okay, there you go. Okay, so I'm trying to share my screen. Oh, actually I haven't finished it, watching it, so. Yeah, let's do this. I'm gonna just kickstart it, and I will try to update you on the previous part, like 2/3 of the video, basically 60% of the video I watched already. So I suggest we watch the rest of it. How do you like that strange plan?
Okay.
Yeah, I love how open you are to all ideas. Okay, but the problem is, can you hear?
Physicists unable to resolve the...
Can't you hear the sound?
No.
The structure of extra dimensions are only sensitive to gross features. It is not that there can be no information, but the information is limited. A bit like trying to describe one's daily life using a vocabulary limited to 100 words. We could say something, but think how much would be.
Now, okay, let me switch to a headset. I mean, back to the speakers so you can hear anything.
Maybe I'll open it on my YouTube.
Yeah, but I need to solve this problem. I want to demonstrate it on Friday, so this could be also a test drive.
Okay.
Left out.
Yeah,
If we
now I
blur
know.
the ability to perceive extra dimensions, then just before reaching nothing at all, the last thing we would be left with would be particles. This is a statement of the mathematics, and it also follows from the mathematics that the number, type, and interaction of these particles would reflect the geometry and topology of the extra dimensions. And although there may be exceptions, it is generally true that the more complex the topology of the extra dimensions, the larger the number of such particles that would survive. These particles would be the minimal quantum excitation of the extra dimensional geometry.
So this is a pretty cool physical model, like mathematical model that geometrically looks like this. So this is one of the ideas, one of the suggestions from different physicists that came up with this shape. I think there are two scientists who proposed that this is Richard Feynman. Do you remember him?
Yeah.
So yeah, he came up with one idea. So the whole video is actually just like step by step taking you through different, ideas and different developments of these, physical theories. So you start from introduction, like what physics is and all of that, and then like some integrated advertising, as we can see the fifth dimension. So it was like revolutionary at that time, and Einstein and all of other scientists, they didn't accept it. So a lot of time later, this other scientist, he started like during the World War II, some other. So it's like science is like a long process, and some papers might take like 10 years or 15 years before they get more recognition, I would say. So this guy's last name is Kaluza, what was the Kaluza? Yeah. So this is a different name. So the second part is part 2, the theory of strings. So this was about string theory, that there are many spaces that are like, I imagine it as if there are many universes. So the universe is very vast. Imagine like a huge space, which is mostly empty. 99 something % of space is just emptiness, boring and empty. And just like very little fraction of the universe is actually material stuff. And that's why because our mind and the way it works, we are bored of emptiness. That's why people, when they try to explain what's going on in the world, in the universe, when they listen to that, they tend to memorize and remember only the parts that concern space, not space, but material stuff. Something like planets. We're much more interested in planets than gaps between them, right? So the string theory is the idea is that there are multiple universes. As maybe I'm wrong, because this is what I think of the multiverses. That there are like these universes are multi-layered somehow. There are like many levels, and they are trapped in a bigger structure, something like this, which could be limited in space. But look at the structure; it has a lot of holes. It means that this topology is very useful. It doesn't take much space, but it's like a finite number of space it's going to take. But it can work. You see, like some of the parts annihilate each other, so they're like particles and antiparticles, and that's why they destroy each other. That's why there's always movement. There's always something going on. It feels like infinite, but at the same time, you can come up with these topologies that could be finite, but at the same time provide an infinite space for something, like for experimentation, I would say. So yeah, let's continue.
Theories of extra dimensions, they are to the extra dimensions a bit like what the photon is to light and electromagnetism, the minimal quantum lump that is left. And so these particles would be legacies of a higher dimensional theory of gravity when viewed from a lower dimension. And so, this leaves us with questions. What are these legacy particles? If they exist and are generic features of theories with extra dimensions, surely we should be able to detect them. To begin with, let's focus on the most interesting and most generic type of such particles, a modulus.
What?
Modulus particles, in their plural moduli, originate from describing the size and shape of extra dimensions. Why, then, can we not just try and observe moduli by making them in particle colliders such as the CERN Large Hadron Collider?
Look at that. This is something that you used. CERN. Do you recognize it? It's a particle accelerator or a Large Hadron Collider, which does exactly this. They use some of the distance to speed up two particles and crash them together and see what's going to happen. So they see this experiment actually helps you to understand to rewind time and to understand what was the state of this space and time and particles in the beginning of the universe.
Why not just smash particles together at high enough energy in order to make moduli and thereby discover them? This, after all, is a long-established approach for making and discovering new particles. The problem with this approach lies in the origin of moduli from extra-dimensional modes of the graviton. Such moduli behave like gravity, and gravity is, by far, intrinsically the weakest of all the forces. Gravity is such an incredibly weak force that when you put your little finger inside a keyring and lift up the ring and its keys, you are able to pull the ring up against the gravitational pull of the entire Earth. This shows just how extraordinarily weak the interactions of the gravitational force are, compared to any of the electrostatic effects used by our bodies and muscles.
Isn't that cool?
The
like, in some sense, gravitationally, like, one of the fundamental physical laws, you can basically be more powerful than the Earth. Pretty cool.
Gravitational force is therefore far, far too weak to be probed directly at any particle collider. Particles whose interactions are gravitational could never be produced, even by a collider, running at full intensity from the time of Stonehenge to now. Their interactions are much weaker even than neutrinos, which famously can pass through the entire Earth without interacting with any of the matter on the way.
Doesn't care. Actually, in Kabardino-Balkaria, there's a settlement
So,
called Neutrino.
what can we do? Perhaps extra dimensions and moduli may exist, but perhaps we can never observe them. If a collider can never make such particles or reach the energies required to resolve extra dimensions, would they always exist as some form of inaccessible other shadow world which we could never actually detect? But it is not yet time to indulge our worst fears. It is true that interacting so weakly, moduli would be very hard to make in the first place. However, this has a positive counterpart. Once they have been made, moduli would also live for a long time. The weaker the interactions, the harder it is for a particle to decay. Particles which interact via the strong force are easily made, but they typically decay in a lifetime much less than a billionth of a second, whereas equivalent particles whose only interactions are at gravitational strength could have...
Обратил внимание, с предметами часто whose делают почему-то. Интересное такое.
С чем?
Да, particles в множественном числе, они же не живые, но используют вместо that whose или which, мы же привыкли that и which. Я часто замечаю, что whose тоже используется к предметам причем. Давай отмотаем буквально на одно предложение. Much less than a billionth of a second, whereas equivalent particles whose only. Yeah.
As equivalent particles whose only interactions are at gravitational strength could have lifetimes measured in years. But still, to make them, we would need extreme conditions. And the most extreme conditions in the history of the universe occurred in its first moments.
Occurred, типа должно быть occurred, через ее почти все произносят.
Oh
In the
no, we
beginning,
lost
it is
our
believed,
listener.
if not known for an
Oh.
absolute certainty, that the universe underwent a period of cosmological inflation. Its size grew both rapidly and exponentially in an extremely short period of time. It is hard to overstate the speed of this growth. Indeed, in the inflationary epoch alone, the universe is believed to have doubled its size approximately 80 times. Within a time period shorter than it would take light to cross from one end of an atomic nucleus to another, a length corresponding to the size of that atomic nucleus would have grown to a size far larger than that of the Earth. At the end of this inflationary epoch, the enormous energies present in the universe were transferred away from the energy of the inflation into particles, both making them and flooding them with energy. At the immediate end of inflation, the result is an enormously energetic soup with potentially many different types of
What? I think I might have jumped into... Are you still in spatial? Yes, you are. Okay. Can't you hear anything?
particles, and these energies present
there you
during
go.
inflation are associated
Hold on a second. I thought yeah. I rewinded it back. Can you still see it on the screen?
Yeah.
inflationary epoch alone, the universe is believed to have doubled its size approximately 80 times. Within a time period shorter than it would take light to cross from one end of an atomic nucleus to another, a length corresponding to the size of that atomic nucleus would have grown to a size far larger than that of the Earth. At the end of this inflationary epoch, the enormous energies present in the universe were transferred away from the energy of the inflation into particles, both making them and flooding them with energy. At the immediate end of inflation, the result is an enormously energetic soup with potentially many different types of particles. And these energies present during inflation are associated with space and geometry itself. In Einstein's theory of relativity, geometry and gravity are almost one and the same, and moduli are the particle excitations of geometry, or at least of the geometry of the extra dimensions. And so if moduli do exist, when inflation ends and the inflationary energy is transferred to particles, it would be natural for at least some of this inflationary energy to be transferred to the moduli. These share in the post-inflationary bounty. They are made, they exist, and they would form some part of the maelstrom of particles in which the energy of the universe is deposited straight at the end of the inflationary epoch. And it is here that the long lifetimes of the moduli matter. Moduli would live much longer than other particles, and so if this scenario is true, they would, in time, come to dominate the energy density of the universe. Eventually, if only for a moment, almost all of the energy in the universe would be in the form of moduli. You can think of this a bit like a hammer striking a great bell. When first struck, the bell rings with the rich, deep sound that comes from the many harmonics and overtones present in the bell resonating at once. But as time goes on, the higher harmonics decay and can no longer be heard. Several seconds after the original strike, the notes that remain are the longest-lasting harmonics. In the same way, in the early universe, the particles that
Likewise.
live the longest are those that are left when all else has decayed. Estimates predict that less than a yoctosecond after the Big Bang, most particles would have decayed, but that moduli would last for nearly a full microsecond. A relative eternity.
Yeah, this is like, micro, macro, and mega. Like, there are 3 levels. Isn't this amazing, like, how we know this about science? Like, it's just like, listening to this information makes me awe. Like, it's like, so cool. Look at this, like, do you remember the Big Bang Theory? So, like, the first second, basically, just, in other words, the first second was such a short period of time, but at the same time, like, so many levels of things happened in just this fraction of a moment. So Can I share my like crazy idea with you that just came to my mind?
Yeah, of course.
There was like a film that is called Scanner Darkly, and I liked one of the dialogues that they had. Like, doesn't really matter. Two people were talking about life, and she said, "What do you know how people say that when you die, like your life flashes before your eyes, and you remember everything that happened in your life?" He's like, "Yeah," and she said, what if we are like memories, like everything we see as a reality?" We are right now are memories that some old lady is looking through in her last second. And I'm like, wow, that's a pretty cool idea. Like, imagine if when you die, for example, that one last second of your life basically becomes an eternity, which can fit in so many different, like, notions, including the universe. Like a Big Bang could happen while you're dying. So that's a crazy idea. Okay, so let's move on. A relative eternity. I like the way he put it. Like, that was a yoctosecond. This is the first time I learned this word. So estimates predict that a yoctosecond after the Big Bang, most particles would have decayed. But the moduli would last longer for nearly a full microsecond. So microsecond is like what? 19 times more. 19 zeros more times. So do you remember these periods like -6? It means that it's like 1 millionth basically.
Yeah.
Because there are 6 zeros. Oh, it's so convenient to talk to smart people. Okay, let's continue.
Eternity. By itself, this might not seem so significant. Energy is conserved. When particles decay, their mass energy does not simply disappear, but instead gets converted to other forms of energy, in particular relativistic particles such as photons, the quantized version of light. But as our new universe expands, energy in the form of relativistic waves, such as photons, dissipates rapidly. The reason for this is something called the Doppler effect. This effect refers to how the pitch or frequency of waves change depending on whether the source of the wave is moving towards us or away from us. It is most familiar to us from ambulance sirens. Although the siren itself operates at the same intrinsic note, when the ambulance is driving towards us, we hear the note at a higher pitch, and when the ambulance is driving away from us, we hear the note at a lower pitch. To an observer located at some point in an expanding universe, the expansion is like having everything move away from you. A continual growth in space itself means that every other point in the universe is, all the time, constantly moving further away. In these circumstances, all forms of relativistic wave energy feel the Doppler effect. As the universe is stretched, the wavelengths too are stretched, and so the frequencies, the inverse of wavelength, all decrease. For light waves, that is, photons, the energy of the photon is directly proportional to its frequency. As the universe expands, the frequency decreases and the energy decreases. But for moduli, the same would not be true. Moduli would be heavy and their energy associated to their mass and not to their movement. The mass energy of a modulus would all be concentrated in the particle itself, rather than its motion. These heavy particles would not be relativistic and would simply remain where they are until they decay. While the universe expands, they stay right where they started, maintaining all their mass energy until the point at which they eventually decay.
Decay.
Meanwhile, all the other particles, who have their mass energy associated to their motion in the form of relativistic particle waves, have all this energy dissipated away to the Doppler effect. And so, if moduli do exist, it is likely that the universe went through a comparatively long phase just after inflation where its energy was dominantly in the form of the mass of moduli particles. For almost a microsecond right at the very start of the universe, the moduli had their day. Almost all of the energy of the universe in the form of quantum excitations of extra